Hi everyone. In this video we are going to cover section 4.5, derivatives and the shape of a graph. And we start out with the first derivative test, and the theorem is at the bottom of the screen, but I just want to draw a picture real quick and explain why hopefully it makes sense. So if I graph a function, right, and all we know about the function is that the derivative is greater than 0, meaning that the derivative is positive, that tells me the slope is positive, and therefore the function must be increasing. So if this point here has a positive slope and this point over here is another one that has a positive slope, the derivative is positive, then the function from left to right must be going in an upward direction. All right, even if I draw it a little bit differently, on my axes, and from this point here to this point here, A and B, even if I draw it a little bit differently, if my derivative between A and B, f prime is positive, and then at B, f prime also positive, right, we can see that if those two slopes there are positive, then the function from left to right is going up, is increasing. Okay, so that's kind of the underlying theory behind, or the visual behind the first derivative test. And what the first derivative test says, that if f prime changes sign from positive to negative, then f of c is a local maximum. So at some point c, some critical point that we talked about previously, if my derivative changes sign from positive to negative, then we have a local maximum. Okay, so what that would look like, if I continue my graph on the right, here my slope is positive, but if I then add a point that I'll call C right there, if my slope changes to negative, over here f prime is negative, the slope is negative, at that point C right there, we have a local maximum. Okay, and then moving on to part 2, if the derivative changes sign from negative to positive, then we have a local minimum. And if I extend my graph on the left a little bit to the left, actually, we can kind of talk about that. Here, my f prime is negative, and then at some point C there, it changes from negative, the slope changes from negative to positive. So f of c is a local minimum. And then the third part there says that if the derivative has the same sign on either side of the point C, then it has neither a local max nor a local minimum. All right, so let's take a look at a picture and investigate this graph here. So here we have some function, and we've got, well, here, my pointer, along this section of the curve, the derivative must be positive because all my slopes are positive. Here's an example of where the derivative would be undefined, but to the right of that, all of the slopes at each of these points would be negative until I get to this point B here. And then at that point, I have a horizontal tangent line. The derivative would be 0. And then to the right of that, the derivative goes back to positive. So we've gone from decreasing, negative, to positive, increasing. So the derivative, so that B is a local minimum. And then to the right, here we have our function increasing. The derivative is positive. At this point C here, we have a case where we have a horizontal tangent line, but the function stays increasing from the left and then increasing to the right of that horizontal tangent line. So just because we get a critical point, it doesn't necessarily mean that you're going to have a max or a min. It just means it's a possible one. All right, and then as I continue on to the right, we're increasing, positive slope, horizontal tangent line, 0 slope, and then to the right of that, we switch to negative slopes, decreasing, making D a local maximum. Okay, so that's the visual and how we can take the first derivative test, and that's really the first step here, is to take the first derivative test and draw conclusions about what the graph of f looks like. All right, we'll look at our first example here. We're given a function, f of x is equal to x cubed minus 3x squared minus 9x minus 1. And we need to use the first derivative test to find the location of all local extrema. All right, and so what we do, the steps here, first we'll take our derivative, 3x to the second, 6x to the first power, minus 9. We'll set that equal to 0 and solve. Notice I have a common factor of 3, x squared minus 2x, minus 3 equals 0. Keep that 3 out in front, and factor our trinomial into two binomials. X minus 3 times x plus 1 equals 0. And we get two critical points, x equals 3 and x equals negative 1. Now, just as a side note, this 3 came from that factor. The 3 that comes out in front, the GCF from the beginning, that doesn't produce any solutions because that doesn't have an x next to it. I could just take both sides and divide by 3, essentially canceling that guy out there. Okay, so then the next step, what we do with those critical points, and I like to draw this next step on a number line, is we're going to take this number line here, and I'm going to add my two critical points in an order that makes sense, add them onto the number line, and then I need to test and see what the derivative is doing. Not at those points. If I plug those points into the derivative, I'm going to get 0. It's a critical point. I should get 0. But I want to know what's happening between, inside of each of these three intervals. Okay, does the function change from increasing to decreasing? From decreasing to increasing? Like, that's what we're going to find out here. So we're going to take f prime, the derivative, at, say, negative 2. We're going to take f prime at 0. And f prime at 4. Okay, if you plug in 0 into the derivative, you should get negative 9. So that is less than 0. That means the derivative is negative, and the function is decreasing. Decreasing. If you take negative 2 and substitute it into the function, I'll do this off to the side here. 3 times negative 2 squared minus 6 times negative 2 minus 9. That's 4 times 3 is 12. Plus 12 is 24. Minus 9 is like 15. The actual number isn't as important as its sign. It's positive. It is greater than 0. Tells me that the function is increasing. And then last, we'll substitute 4 in. Oops, 3 times, there we go, 4 squared minus 6 times 4 minus 9. 4 squared is 16 times 3 is 48. Minus 24 minus 9, I don't think that's going to be enough to make the answer negative. It's going to be like 15 again, I think. Don't quote me on that, but try typing it into your calculator and see what you get. The big important thing is that it's positive, and therefore the function is increasing. So what does that mean about the function? Well, from negative infinity to negative 1, we are increasing, I'm abbreviating there. Between negative 1 and 3, we are decreasing. And from 3 to infinity, we're back to increasing. All right. So if we switch from increasing to decreasing at negative 1, well, that means that when x equals negative 1, we have a local maximum. And when x is equal to positive 3, the function changes from decreasing to increasing. That means we have a local minimum. Okay, so that's how we use the first derivative test to find our extrema. All right, now we'll look at one other example where we use the first derivative test, and our function this time is f of x is equal to 5x to the 1/3 power minus x to the 5/3 power. Okay, we want to find our local extrema, so that means I need to take the derivative. That would be 5/3 x to the negative 2/3 minus 5/3 x. 5/3 minus 1 is positive 2/3. X to the positive 2/3. So that is our first derivative. And then the next step is to set that equal to 0 and solve. Now, in order to solve something like this, this is a little bit ugly with the negative exponent there. But what we'll do is we'll factor out the 5/3 first, and then we can kind of forget about that because we could divide both sides of the equation by 5/3. And I'm going to rewrite that negative exponent into the denominator. X to the 2/3 is still up in the numerator equals 0. And then I want to take those two terms and write them as one single fraction. Okay, I'm going to do that up over here. So this becomes, again, the 5/3 I can divide out on both sides. This becomes as one fraction, 1 minus x to the 4/3 divided by x to the 2/3, x to the 2/3, and it's still equal to 0. And where that 4/3 came from up in the exponent is this x to the 2/3. To get a common denominator, I need x to the 2/3 over x to the 2/3 like that. Okay, so that's why that exponent is now 4/3. All right, and if I'm solving that, well, I have a fraction equal to 0. Okay, so I am going to, when is a fraction equal to 0? Well, that would be when just the numerator is 1 minus x to the 4/3 equals 0, and add the x to the 4/3 to both sides, and what you end up with is x is equal to plus or minus 1. Okay, because we have the fourth root there, we could get a positive 1 or a negative 1. But those are critical points, right? Like that. It's critical points. And one additional piece, we need to consider when the derivative is undefined for our critical points also. So x equals 0, that is when f prime is undefined. Okay, so same idea as the first one, just this one goes a little bit more involved because it involves a fraction or a negative exponent when we take our derivative. Okay, so we want our critical points. That comes from the derivative equal to 0, and also where our derivative is undefined. Those are our possible critical points. So the next step, and this is like the new piece that we're adding in, is draw a number line, add all of our critical points onto it, and then test the derivative at some point inside of each of those intervals. This would be negative 0.5. This would be positive 0.5. And then I can test 2, f prime of 2. And the number, sure, great, is cool. But what's more important about it is the sign. So I'm not going to take the time to like type these into my calculator in the video because that won't be very entertaining. But you should test the derivative at each of these points. If you want to pause the video now to do that, great. But I'm going to go ahead and tell you what you end up with. So for f prime of negative 2, you get something that is less than 0, telling me that my function is decreasing. F prime of negative 0.5, you get something that is greater than 0, telling me that my function is increasing. F prime of positive 0.5, we also get something that is greater than 0. We are increasing. And f prime of 2 is less than 0, telling me that we are decreasing. Okay, so that's what we get for the derivative at each of those points. Now analyze them. What are they? X equals negative 1 is a local, I can write, there we go, is a local, well, decreasing to increasing, local minimum. X equals 0 is nothing, or well, let's say is not a max min point, is not a max min, and then x equals positive 1. If we change from increasing to decreasing, that would be is a local maximum, like that. The next part of the section deals with a term called concavity. Okay, so if my function is differentiable over some interval and the derivative, notice there's a little apostrophe there, the derivative is increasing, then f is concave upward. If the derivative is decreasing, f is concave downward. Okay, so what do we mean by that? Let's take a look at this first picture, part A. Slope there, kind of flat. Slope here, much steeper. So the derivative, the slope, is increasing. That's called concave upward. Here I have a steep slope followed by a flat slope. The derivative is steeper, flatter. The derivative is decreasing. That's concave downward. The next picture, the derivative is negative and steep, negative and flat. The derivative is increasing, so that is also, like the one above it, concave upward. Here we have negative and flat, negative and steep. Derivative is decreasing, going downward, so that is concave downward for that one. All right, so concave downward, actually let me put this off to the right here. Concave downward, we think of a bowl like that, and concave upward, we think of a bowl going upward like that. All right, so those are two visuals for concave downward and concave upward. So then we get to our test for concavity. If we take the derivative twice, so if f is twice differentiable and the second derivative is greater than 0, we're concave upward. Second derivative is less than 0, or concave downward. So the same idea as the first derivative test and what we were doing in the first two examples, we're going to apply that same concept now to the second derivative of our function. So we'll define one more term in this section, and that is an inflection point. Inflection points are kind of like critical points coming from the second derivative. Basically, if I have a function that's continuous at a point and the function changes concavity there, then that point is called an inflection point. All right, and so it's like the max-mins that we find from the first derivative, but they come from, inflection points come from the second derivative information. Okay, so here is an inflection point. The reason it's an inflection point is because I'm concave upward like a bowl right there. I'm concave downward like an upside down bowl right there. And at this point right here, a comma f of a, the graph changes concavity from the derivative increasing to then, after that point, the derivative decreasing. All right, so that's called an inflection point. So let's go through now an example where we, for our given function, determine all of the intervals where the graph is concave upward and all the intervals where the graph is concave downward, and then we'll list inflection points. Okay, so let's take a look at this one. Our function, f of x equals x cubed minus 6x squared plus 9x plus 30. The first derivative gives me information about slopes, 3x squared minus 12x plus 9. If I set that equal to 0, I find those critical points. Second derivative gives me information about concavity. That's the new part that we're into in this section. 6x minus 12. If I set that equal to 0, I'm going to find a possible inflection point. 6x is equal to 12. Divide by 6, and I get that x is 2. Okay, so at this point, I don't yet know for sure. That may or may not be an inflection point. And what we do is same deal as with the first derivative. We'll draw a number line, put my critical point. It's not a critical point, it's a possible inflection point. Put that point that we found from the second derivative on my number line, and then test something on either side of it. So f double prime of 0 and f double prime of 3. And the actual value is not that important, the actual number that I get, but its sign, is it positive or negative? By the way, if I take f double prime of 2, I'm going to get 0, right? That's what we just found in the previous step. So if you plug 0 into the second derivative, 6 times 0 minus 12 is negative, therefore less than 0, which means we are concave downward at to the left of 2, from negative infinity up to 2. And then if you take f double prime of 3, 6 times 3 is 18 minus 12. That is positive, greater than 0. Therefore, we are concave upward to the right of 2, from 2 to infinity. And we can write this in interval notation, as I did with the earlier example. Negative infinity to 2, we are concave downward, just kind of abbreviating there. And then from 2 to infinity, we are concave upward, again abbreviating. Okay? Great. And now we close out the section with the second derivative test. The second derivative test is another way to identify max mins, and it's a quick one, especially if the function is easy to take derivatives of. So it says if I have a critical point, a point where the derivative is equal to 0, and the second derivative is continuous over an interval containing that point. Basically, I can substitute that point into the second derivative. If the second derivative is positive, we have a local min. If the second derivative is negative, we have a local max. If the second derivative is 0, then the test tells us nothing. The test is inconclusive. Okay, and so the reason that those will hopefully make sense, if the second derivative is positive, that means we are concave upward, so my critical point has to be a minimum. If the second derivative is negative, that means that we are concave downward, and my critical point has to be a maximum. Okay, so that's why the second derivative is hopefully makes sense. And again, it's a quick check, if you will, to tell whether the function is, or whether the function is a max or a min at that point, rather than needing to use, a point on either side of the critical point as we did at the beginning of the section. Both are useful. This one is just has its own specific applications. So second derivative to find the extrema, my first derivative, f prime of x, 5x to the fourth minus 15x squared. We'll set that equal to 0. We'll factor 5x squared from both terms. We're left with x squared minus 3 is equal to 0. And then this gives me 3 different points. X is equal to 0, and x is equal to plus or minus radical 3. So earlier in the section, what we would have done is drawn a number line and then tested on either side of 0 and on either side of those radicals to see whether the function switches from increasing to decreasing or the other way around. But now we can use the second derivative test. So we first need our second derivative, which is f double prime. 5 times 4 is 20. X cubed minus 15 times 2 is 30x to the first power. And then what we'll do is evaluate that second derivative at 0, at negative square root 3, and positive square root 3, and see what we get in each case. And I'll just tell you, when you plug in 0, you get 0. You should check these, do the substitution, do them in your calculator. You get 0, and you get negative 30 radical 3, and the positive square root, you get positive 30 square root 3. All right, so what does that, each of those things mean? This tells me that 0, the test is inconclusive, so we don't know if that is a local max or a local min, or it could be neither. All right, and when the second derivative is negative, and I like to draw it every time, it means we're concave downward. Therefore, this at x equals negative root 3, that is a local max. And then when it's positive, it means we're concave upward. So at x equals positive root 3, that is a local minimum. Okay. Again, I think that the pictures for this one, even though they're quite simple to draw, they just help to solidify, because it's kind of opposite. When it's negative, that's a max. That's kind of confusing, it's or counterintuitive maybe, but it's because the graph looks like that. All right. Cool. So that is the end of the section. Go work on some homework problems. Please send me questions if you have any. Thank you very much for listening, and have a wonderful day.